Hi, welcome to the 6Xonline introduction presentation. My name is Peter Foster. I do reservoir simulation support for Ridgway Kite in Houston. This presentation will be about 60 minutes. So first of all, let's talk about why we would simulate. A lot of people do rate transient analysis. It's a very popular way of predicting reservoirs. It can rapidly generate a huge number of realizations, allowing the analytical model to be matched to historic rates and production predictions to be forecast. However, it's based on some assumptions which make the approach less physically rigorous than numerical simulation. For example, the produced fluid is considered to be single phase, which is a simplification of reality because you would actually have frac fluid come back and then oil, and then when the pressure drops, you may get gas coming out of solution. So the simulation model, rather than assuming that's just a steady standard fluid, can model it as multi-phase black oil or compositional equation of state description, black oil or compositional. With rate transient analysis, the reservoir is assumed to be homogeneous, whereas 6X can work with a heterogeneous geomodel, such as one which could come out from Petrel. So you have spatial variation in the geological structure and the input properties. Finally, RTA generally assumes that the conductivity of the fracture is a constant, whereas 6X has a dynamic process by which the fractures grow and propagate and then close up when the pressure drops. So the simulation method is the only way to capture all of the physical processes that contribute to the production performance. So that's what we're going to look at now, is that 6X simulator. So 6X integrates the flow with the frac design and the geomechanics in a single model. It supports multi-well models, black oil fluids, compositional fluids, etc. And as we said, it is based on a definition of the geology, which can be as simple or as complex as you like. We also use a definition of the fluids, which can be the black oil PVT or a compositional equation of state. And we put in the initial stress state. We then model the injection rates from the pumping schedule at the times and at the locations along the well where the stages were actually fractured. We then model the flowback of the frac fluid and the long-term production. So 6X focuses on field management decisions that influence the production performance, and it can support workflows such as well placement and spacing because it captures the interference between the wells during the fracking and due to depletion. It can also support stress shadowing. It supports completion design workflows where you can change the operational details of how the stages and the clusters within the stages are treated or placed and the impacts of that on your performance. We can also support multi-well gas injection projects where we're doing huff and puff with a compressor and pumping into a set of wells iteratively. We can also do workflows such as refracturing an existing well. So there are very sophisticated workflows that can be handled by 6X. 6Xonline is a web-based application to enable routine workflows. So it supports a subset of those workflows that I mentioned and allows you to build a layer cake model and collate all the data to define the well location, the stage location within the well, and then generate those fractures and produce them. It takes that data, collates it into a simulation case, and runs the 6X simulator either locally or on the cloud. You can also take those cases that it generates and you can save those. You can export them from the application and you can use them as the basis for much more sophisticated models. So you can edit them and customize them. So that's 6Xonline. And let's take a look at what we mean in the simulator, how it integrates the flow, the frac, and the geomechanics. So conceptually, we're starting with, as we said, a geomodel. And on that geomodel, we need to define the stress state, which is the minimum and the maximum horizontal stresses and the vertical stress. Optionally, we can also put in a rock strength, which is an additional amount of pressure which is required to break the rock over and above the amount required to overcome the minimum stress. And then the fracture propagation parameters that we use are these down the bottom here. We have the pore volume expansion rate in microsips, which is how the void inside the rock expands as the fracture is pumped. The tensile enhancement, which is an amount of permeability, which will be added to represent tensile breakage, and a shear enhancement, which is the amount by which the matrix fracture interface, the surface area between those, will be enhanced as the rock breaks. So those parameters all deal with the propagation of the fracs. And then for the closure of the fracs, we have this residual connectivity, which is a percentage of the amount of enhancement that was achieved. So it's the percentage of it which will be retained after the well has been drawn down. Okay, so if we achieve 100 millidarcies of permeability and we say we're going to retain 25% of that, then after the frac has been drawn down by a certain amount of pressure, there will be 25 millidarcies left. So if we put the pressure on the y-axis of a graph, when the pressure increases up this axis, the stress reduces. So we end up at some point overcoming the initial stress that we've marked here. And at that point and beyond, we get negative stress. At the bottom, along the x-axis, we've got the distance from the well. So if we start pumping into the well, we increase the pressure at the well bore. We also increase the pressure out into the reservoir some distance. As we keep pumping, the pressure increases further at the well and also out further into the reservoir. So any point on this graph where we've achieved negative stress is where we're going to have some breakage of the rock. So in this zone here, we're going to add tensile failure and shear failure parameters. And the higher up this y-axis we've gone, the more enhancement we will add. So this volume or this area here represents the extent of the stimulated reservoir volume at this particular location along the wellbore. And the distance from the y-axis across to here on the point at which breakage occurs represents the half length of the fracture at this location. Remember, this can be a heterogeneous model, so the half length may be different at different locations along the well. So if we look at a single point somewhere within that volume, the stimulated reservoir volume, we've got the initial pressure, which is this horizontal red section here. When we start pumping, the pressure is going to increase rapidly. And at some point, it's going to surpass the minimum stress, and we're going to get that negative stress. And we're going to start adding enhancement to the permeability as well as to the shear to represent that fracture enhancement due to the breakage. So depending on how much negative stress we achieve, we get a certain amount of additional permeability. When we stop pumping, the pressure at the location is going to continue to equilibrate. So we'll start to get a little bit of closure. And then when we start to draw down the well, the pressure will drop quickly. And we'll get a corresponding drop in the permeability. So the permeability will be reduced to model the closure of the fracs. The rate at which the permeability is removed is going to be determined by the residual value that we said would be ultimately retained. Okay, so we've got the fracture opening and closing, and that's all linked to the net stress, which is basically a function of the pressure. Okay, so let's have a quick look at the 6Xonline app. So we go to our website, and here's the app. We've got a help screen over here on the left. Then in this column here, we've got the different sections of the application. Models is where we define all the data. Run is where we submit the simulation runs. And plot is where we do the analysis. So we can load up the results, plot pressures, rates, etc. So if we look at the models tab, it's broken down into sections for the reservoirs, which is where we specify the natural world, the rock, the layers, the fluid, etc. The well, the frac jobs that we attach to the well, and the scenarios, which is the timing for when we implement operations. Then there's a build section that lets us put all that together into a simulation case and then go to the run panel to submit it. So all of these panels are loaded with defaults. So we can go directly to the build panel and do check and build, and we will get a model. We can then go and run that model. So we've submitted the model to our queue. We're running it on a CPU. If we do status, we can see the model which is running and some models that were run previously. If we click on the status word over here on the right, it'll tell us how far it's got. So this column here says this has made it to 1,825 days of simulation. So we press OK to exit from that, press status again to update it, and it's finished. So we can then go to the plot panel to analyze it. We do get model, we get that same list again. We click on the summary data column to load it. That model's loaded in, and we can go in and we can plot lots of different types of line plots. So that's the basic overview of the functionality. Let's look at an example of how to put it to use. So for example one, we're going to look at a single stage on a well. So we're going to use a short section of well in a model with one stage on it. And we're going to look at how we input the data, how we build and check, and then analyze that simulation. Okay, so this is what our model looks like. We've got a single layer. The porosity is 7%. The permeability is 1e to the -4, and the layer is 500 feet thick. The well is roughly in the middle of that, depth-wise, and it's a short stub of a well with a single frac in the middle, a single fracture stage. Our fluid is a light oil, and we're in the oil zone, so the gas contact is above us and the water below. So we're going to make sure that those are out of the way. The stresses, we're going to use 9,000 as the minimum horizontal stress and 12,000 as the maximum horizontal stress. The vertical stress, we'll put 14,000. And then for that fracture propagation, fracture enhancement input, we're going to use a pore volume expansion rate of 900 microsips, a tensile fracture of 1,000 millidarcies, and a shear fracture of 2 in terms of the surface area. And we're going to retain none of the stimulated, and 40% of the propped enhancement. The simulator is going to determine internally which parts of the SRV is stimulated and which parts are stimulated and propped. And we'll look at how that's determined in a later example. For now, we'll just trust it. So our well is going to be at 10,070 feet, and it's 300 feet long, and the fracture on it is going to be 150 feet long. We're going to pump it at 20 barrels a minute for 45 minutes, and we're going to produce back at 250 barrels of liquid a day. And we're going to do that for 3 months. Okay. So let's go back to our app and put the numbers in to build this. We're going to load a project called example 1A. And this project has some notes added to it over here on the right-hand side, which will tell us what the data needs to look like. So we start with our formation, which encompasses the depth and the fluid pressure and the contacts. So we're going to leave the depth at the default of 9,800. We're going to set the pressure to 7,200. We'll default the gas oil contact, which means it's going to be up above us, and we'll set the water oil contact to 12,000. So it'll be down below. Now, if we look at our plot here, we can see that we've got our surfaces. So the top surface is where we told it to be. The bottom surface is at some default location. And then the water contact is down at 12,000 where we said. So let's pick a fluid. We're going to use the light oil, which is a built-in set of PVT data, which is similar to an Eagleford oil. You can import your own fluid system if you have one, but we're going to use the built-in one for now. Bubble point of that fluid, the point at which the gas starts to emerge from the fluid, is going to be 4,000. And we're going to plug in those stresses that we talked about. The data can be rotated so that it's not all perpendicular and parallel to each other. So if the well was not drilled along the stress direction, you could specify that here. We're going to stick with 0 for all our orientations so that everything stays perpendicular, parallel, square with each other. So that's our stress states. We've got a single layer, and the thickness of that layer is 500 feet. And the vertical enhancement, the number of simulation grid cells we're going to have in the vertical orientation is going to be 50. If you hover over any of these items, it'll tell you what the units need to be and also give you a longer description of what the parameter means. So associated with the layer is a rock properties definition called rock 1. So rock 1 in turn consists of porosity 1, geomech 1, and scal 1. And these data items are defined from these 3 remaining tabs here. So poro 1, we're going to set it here to 0.07 porosity, 7%. And the permeability, we're going to set to 301. Then the geomechanical parameters, this is where we put those propagation inputs. The rock strength we'll leave at 0. Permeability, we're going to add up to 1,000 millidarcies, and surface area 2. We'll change the microsips, the compressibility, to 900, and we'll set our residual K, the amount of permeability which is retained after drawdown, to 40% for the propped areas, and leave it at 0 for the unpropped stimulated areas. Okay. We don't need to fill in the rel perm data. We can leave that as the defaults. So that's defined our entire geological model. We've now got our surfaces at the places where they should be. We've got our contacts, and we have all the different properties associated with that thickness. So now we need to tell it where to put the well. So we're going to move the depth down to 10,070 and reduce the length to 300 feet. We'll leave the rest of the parameters the same. So now we can see we've got a short stub of a well here in our little thumbnail plot. And if we rotate it, it's kind of in the middle of our layer. So we need to tell that well what the frac jobs associated with it are. So the overall information about the stages, the frac job as a whole, goes on this frac panel here, where we tell it the number of stages, which is going to be 1, the length of the stage, which will be 150, and the spacing, which we'll put as 75. Oops, 75. Then the actual operational information, the pumping schedule, etc., for that goes in this stages panel here. And we're going to say that our pumping rate is 20 barrels a minute. Our duration is 45 minutes. And our time gap is 60 minutes. And for the injection fluid, we're just going to use water. We're not going to specify any special characteristics of that. So we've got our one-stage frac operation, and that stage consists of these pumping parameters. So now that we've got all our data, we need to schedule when those things are going to happen. So on the Scenarios tab, we can set up a schedule whereby well 1 has frac 1 performed on it at, we'll say, time 0, so right at the start of the simulation process. And then after the frac job, we're going to do some production, and we're going to start the production at day 1. And the parameters that control that production are set over here. So we're going to set a minimum bottom hole pressure of 1,000, a maximum rate of 250, an economic limit of 10 barrels. So that's the point at which the well shuts in if it's not flowing enough, and an end time of 3 months, which is a quarter of a year. Okay. Again, you can get the units by hovering over these things. So there's the standard barrels per day, for example, for the production rate. So that gives us all of our parameters. So we can now go to build, and we can put those together into a simulation case. So let's rename our simulation case, call it example 1, and hit go, and do check and build. So it's built it okay. So now we can go and run it. We click on run, change the queue to GPU 1, and run it. So this is going to send it to the server, put it into the queue that accesses the NVIDIA GPUs, and simulate it. So if we do status, here's our job, it's running. And we click here, it'll tell us how far it's got. So we've got to 1 day so far here. So that means that we've done the frac job and we're starting to do production. So if you do status again, we're now up to 30 days. So we're getting through it. We can go over to the plot window and clear this out and get ready to load the results, assuming they'll be finished in a second. And there they are. So we load the results by clicking in the summary column on our case, example1.js for Java script or JSON data. Press OK, and we've got our data there. So it automatically plots our production rate, and we can add in our water production rate. So here's our frac fluid flowing back, the blue line. And when it starts to decline, our oil rate starts to increase. After about a month, we fall off the plateau and the oil rate declines until when we get to the end of our 3 months, we're only producing about 16 barrels of oil a day. So that's the performance that we get for that set of parameters that we gave it. So if we go back here, what I'd like to do now is change the input parameters a little bit, and we'll keep it simple by only changing one parameter and see the impact that has on our production performance, on our pressures. So we're going to change the amount of shear fracturing, which, if you recall, was 2 in the original one. We're going to make that much smaller to reduce the amount of leak off that we get from the fracture into the matrix, and then back from the matrix to the fracture when we do the production. So we're going to build that new case, and we're going to compare it back to the original case. So this is going to do a couple of things. It's going to show how easy it is to create a suite of cases based on an initial set of data. And also it's going to show how we can calibrate a model to change the performance. So we go back here, and the way that we would implement a different set of natural characteristics, if you like, is by creating a second copy of our reservoir. So we'll rename that second copy to reservoir B. And then we go into that reservoir B and we change whatever numbers we want to. So we're just going to change this one here, and we will reduce it from 2 to 0.2. So the amount, the intensity of the shear fractures that are causing leak off is going to be reduced by a factor of 10. So then we can see the impact of that by going straight to build and copying our original model called 1alt. And to incorporate the modified reservoir, we just pick reservoir B off this drop down here. We keep all the other inputs the same because we're not changing anything there. We do check and build. It was successful. And we'll go over and we submit that run to our GPU again. So if we do status, we've got that new version running. We click over here. We're just at the start of the run so far. So we've built that example and submitted it. And when it's finished, we can bring it in here to the plot window, and we can analyze the difference between the original and the new version. So we've got to 90 days, which should be the end. Yep. So we refresh the data, bring it in. And here is our oil rate from our modified versions. The green line is the oil rate from the new one. The red line is the oil rate from the old one. So we can see that we just barely make it to close to our plateau number and then immediately fall off. But we're flowing for longer at a slightly higher rate, but we've lost a lot of plateau time here because of that change to the leak off. Now, if we clear this and select our two cases, we can plot the well bottom hole pressure. So here's the two different well bottom hole pressures. So one of them, the original model, is holding up until about 40 days before it hits our limit. The other one is dropping quite quickly and it's hitting the limit after only 17 days. So what we can do is, if we know what the performance of our real well was in the field, we can match that with our model by changing the inputs and tuning them to the point where we get a calibrated model that mimics reality. So that expected response, measured response, is perhaps somewhere in between these numbers. So we know that our shear factor needs to be somewhere between 0.2 and 2, and we can do more experiments to find out exactly what that value needs to be to get a realistic response from our model. So we can calibrate the model inputs to match historical performance and thereby get a reliable experimental model that reflects reality that we can base decisions upon. So let's see how we could then proceed and test out some operational parameters. But first we'll review those breakage parameters. So as we said earlier, we increase the pressure by modeling the injection from the pumping schedule in the simulation model. So the pressure increases, it exceeds the minimum stress, and the net stress becomes negative. Negative net stress means that the rock is broken and we start adding enhancement. So here's our pressure going along at the initial reservoir pressure and then increasing when we're doing our pumping. At some point in here, it exceeds the minimum stress and we get a negative net stress. When we get that negative net stress, we start adding extra permeability up to either a maximum amount based on our input or a maximum amount based on how much net stress we achieved. When we shut that stage, the pressure will continue to equilibrate, and in some places that pressure will decrease and gradual closure will initiate. Then when we start to flow back, the pressure will decrease faster and we'll start to lose significant amounts of our enhancement. The rate at which we lose the enhanced permeability due to the drop in pressure is dependent on the residual percentage that we put in to our geomechanical properties. So as the pressure drops, we're closing the fractures at a specific rate, and we can tune that rate to match actual observations. Okay. So the minimum stress is this one here on the stress state. The strength is on the geomech panel, and that's the amount of negative stress above the minimum stress that we would need. The maximum permeability addition is this. The maximum rubble generation shear surface area is this one here. And the pore volume expansion in microsips is this one. So these are all the controls on how the fracture will propagate when we breach the initial stress state. How it will close is based on these specifications here, where these are percentages of the maximum amount of enhancement achieved. Okay, so let's look at that operational example. So this time we're going to build a full well with 24 stages. We're going to go through the data input again, build and analyze the results. So we'll look at using a more complex geology. We're going to have two layers here, and the permeability and porosity are going to be different between them. The upper layer is going to have lower porosity, lower permeability, and the bottom layer is going to have better rock. It's going to be a higher porosity, higher permeability. And the well is going to go roughly on the boundary between them. So the fluid is going to be our light oil again, with a bubble point of 3,500 psi. And we're going to set the initial pressure at 7,200. And again, that'll be at the datum depth that's defined by the well location. The stresses are similar to before, 9,200 as the minimum, 12 as the max, 14 as the vertical. And we'll use those same parameters that we've been talking about for the fracture propagation. but we'll change the propped closure to 25%. So our well is going to be at 9,080 feet, which is close to the boundary between those two geological units. It's going to be 10,000 feet long, and we're going to fit 24 stages on it. So if each stage is 300 feet, that implies there's a gap of 120 feet between them. So we're going to sparsely populate the well. We're going to pump into each of those fractures at 20 barrels a minute for 3 hours. And then we're going to allow 2 hours for the turnaround time before we're ready to pump the next stage. So it's going to take a total of 5 hours to complete each of our 24 stages. Then when we finish that, after a certain amount of time, we're going to turn it into a producer. We're going to produce 2,000 barrels of liquid per day, total liquid, for 4 years with a minimum bottom hole pressure of 1,000. So we're going to flow it back and produce it for 4 years, see how much production we get. Okay, so let's go do that. So we're going to load in a project which has some notes that correspond to the data description that we just saw. And we're going to go through, plug that in. So our top depth is 9,000. Our pressure is 7,200. We already saw this once, so I'm going to go through a little quicker this time. 8,900 and 12,000. The water oil contacts. One thing that's new is we're going to put a horizontal refinement factor of 3, which is going to increase the amount of detail in the simulation model so that we can capture all those stages. We'll talk in a later session about how to determine what that needs to be. Our fluid is our light oil again, with a bubble point this time of 3,500. Our stresses, minimum is going to be 9,200. Maximum 12,000, vertical 14,000. Now the layers are going to be a little different this time because we have 2 of them. So over here is where we can put a list of all our layers. So we're going to rename the default layer to top. And we're going to add a second layer that we'll call bottom. So we've got our 2 layers, and initially they're identical. So for the top one, we're going to say the thickness is 100 feet, and the vertical refinement in terms of how many simulation layers, simulation cell layers there are, is going to be 5. And it's going to use rock 1 as the definition of the characteristics of the geology, the geomechanics, etc. The bottom layer is going to be 120 feet thick. Again, we're going to use 5 simulation layers to represent that. And the rock definition, we're going to create a new item called rock 2 so that we can make it different to the top layer. So here on the rock tab, rock table, we've got rock 1 and rock 2. Again, they're the same right now because we haven't told it anything else. But what we want to do is set rock 2 to have a different porosity and permeability. Remember, we said top has 2% porosity, 1e to the -5 permeability, bottom has 5% porosity and 1e to the -4 permeability. So we'll go up here and we'll say we'll create a new item for porosity, PORO2. So now rock 1 uses PORO1, rock 2 uses PORO2. So let's plug in the numbers for each of those. So porosity 1 needs to be 0.02 for 2% and 1e to the -5. PORO2 is going to be 0.05, 5%, and 1e to the -4. So there's the difference in geology between the 2 layers. The geomechanical properties that control the propagation, we're going to set them the same. So the strength The tensile and the rubble are all the defaults that we used before. We're going to increase the compressibility to 900 and set the residual to 25%. And again, we're going to leave the rail perms as defaults. So we've got our two layers, and if we zoom in on our little thumbnail sketch over here, we can see our gas oil contact, our top layer, our middle that divides the two units, and the bottom of the base unit, and then down here is our water contact. Our well is currently hovering somewhere below our reservoir, so we need to go and move that to the right place. So we click on wells. I tell it the depth of the well is going to be 9,018. So we submit that, and the well has jumped up into where we want it, which is in between our two layers. We'll leave the orientation and the length and the deviation from the vertical as the defaults. So frac jobs. So we're going to have a frac called 24 stages. And we're going to put 24 stages on it of 300 feet length and 120 feet spacing. Okay. Now, each of those stages are going to be treated like this. So we're going to say a rate of 20 barrels a minute for a duration of 3 hours, 180 minutes, and a gap between them of 120 minutes. The injection fluid this time, we want to give it a viscosity of 0.5 to mimic a slick water. So we'll go to injection fluid. We'll rename the existing water to slick water. And we'll reduce the viscosity from 1 to 0.5. And then go back to our stages and make sure that we're pointing our injection fluid to slick water, and we are. So that should be ready to go. We've got 24 stages, 300 foot long, pumped at 20 barrels a minute using 0.5 viscosity water. So our scenarios, we've got a schedule which applies our 24 stage frac to our well at time 0. Then after 20 days, it produces using the criteria specified in prod 1 over here on our second tab. So our bottom hole pressure is going to be 1,000 minimum again. The maximum barrels a day of liquid is going to be 2,000. And we're going to set a 20 barrel a day economic limit so that the well will shut in if it can't handle that. We'll run this for 4 years. Okay. So there's our schedule. So go to build, put all that together. First of all, we'll rename the model to 24 stages. We'll check that. We've got no errors and no warnings. We're using the 24 stage frac using slick water. We've got our 2-part geology with our upper and lower layers in it. Okay. So we could go run that, but it'll take a little while to run. So let's go and load one that we did earlier, that I did earlier. So do get model, and we can click on this 24 stage example 2 here. And we can plot that directly. So here's the oil production rate that we got. So the plateau lasts 550 days and then declines quite quickly. If we clear that and go in and plot the well bottom hole pressures, we see the pressure decline over the life of the well. And if we restrict the x-axis to just the first 5 days of the run, we can see the individual fracs being performed. So each of these should be 3 hours of pumping followed by 2 hours of turnaround time before the next one starts pumping. So there's all our fractures going in. So we can go in and show how much actual production we got. FOPT is field oil production total, and there's our total production after 4 years. Okay. So we've shown that we can build a 24-stage model, and now we're going to go in and edit that model to vary the stage count. We'll keep the same stage length, but we'll vary the distance between them and thereby get different number of stages fitting on our well. And we'll see how that impacts the production. So this is to show that we can experiment with the operational parameters. So let's load in a model where we've already done that. So that will be this one here, example 2 done. So here we've got, under frac jobs, we've got a 16, a 24, and a 32 stage job. The actual stages are all pumped the same way as before, 20 barrels a minute for 180 minutes, and then a gap of 120. The only difference is that we have a different number of stages. So for each of those different operations, we have a different scenario set to control it. So we've got a scenario which uses the 32 stage frac, and one that uses the 24, and one that uses the 16. So we can build all of those models and submit them and run them. So as before, I've already done that. So we can go directly in here and do get model and see the results of those different setups. So there's the 16 stage one. There's the 32 stage one. So if we clear our background, select our 3 wells and plot our rate, we can see that our original one stayed on plateau for about 550 days, if you recall. The 16 stage one only stays on plateau for 1 year. The 32 stage one also stays on plateau for about 550 days, but it doesn't drop as precipitously as the 24 stage one. It holds up a little bit longer and then goes into decline. So we can see the impact on the cumulative production, the field oil production total of those changes. So there's the ultimate production, 780,000 barrels, 1.13 million, 1.27 million, depending on how much we frack the well. So that's kind of shows just how easy it is to take a basic model setup and create variations on it to explore different decisions, different operational setups. Okay. So this is kind of a summary of what we got there. So the point is that once you've got a calibrated base model, you can use that as an experimental model to assess the impact of different management decisions on how you operate the well. And you can get out all of the parameters that you need to then go to do an economic analysis and make a financial decision of what is the best way to proceed. So we changed the number of stages. You could also change the rate or the duration of each stage to model different sized jobs. And of course, you could also have different geology underlying the whole thing, so you could have uncertainty on that side as well. And you could get all the different outputs to allow you to make a sensible decision. Okay. So we've shown that we can experiment with alternate development strategies and use our model to evaluate their impact on our production. and we can tie that directly to a financial model to make sensible decisions. So to summarize what we've seen today, we've used a single well, single stage model to show how we can calibrate the results of our simulation to match reality by changing the underlying geological and geomechanical properties of that rock. In other words, to change how the fracture propagates and closes. We've also shown a single well, multiple stage example that showed how we can experiment with different management decisions to change the design and assess the impact of the different designs. So that's all we have for today. If you want to know more information, please contact me at this email address here. If you're interested in getting access to 6Xonline, contact Tommy Miller at this address, or you could go to our website here. So we'll be back with the next presentation after the spring break. If you have any questions in the meantime, please feel free to get in touch with us at either of those contact addresses. Thank you.